In today's lecture, we will be discussing the unbalanced magnetic pull and its effects in electrical machines. Let's see what is unbalanced magnetic pull. In rotating electrical machines, if the air gap around the armature periphery is non-uniform, then radial forces are developed in the rotor. The radial forces will be perpendicular to the rotor axis, and this force is called unbalanced magnetic pull. Next, we will derive the expression for unbalanced magnetic pull. First of all, we will consider a machine with a simple north and south pole only, in which, due to the attraction between these poles, one of the poles has shifted by through a distance dx, a small distance dx. Here, the north pole has shifted through a distance dx. So, if one of the poles is moved by a distance dx, then the work done will be equal to the change of energy stored in magnetic field. First, we will obtain the expression for work done. Work done is equal to force into displacement. Force means magnetic force. Then the right hand side of the equation is change of energy stored in magnetic field. That is, the change in energy is equal to energy density into change in volume. That is equal to half b square by mu 0, that is the energy density, into the change in volume, that is AP into dx. AP is the area cross section of the pole, one of the poles which shifted through a distance dx, and dx is the distance traveled. So this is the volume. This dotted line between these two dotted lines, this portion is the volume, change in volume. So thus change in volume is the product of area and distance. So let's equate those two values. On the left hand side the work done, and on the right hand side the change in energy. By rearranging, we will get the equation as F is equal to half b square by mu 0 into AP. That is equation number 1. Here F indicates the force of attraction between the north and south poles. Now let's consider a machine in which rotor is not concentric with stator. The force of attraction between the top stator and rotor poles is given by F1 is equal to half B1 square by mu 0 into A. This equation we have already derived in the previous section. Here we can see that this is a machine with stator is not concentric with rotor. So the air gap on the top portion is more as compared to the bottom portion. So that means Lg1 is greater than Lg2. And here we have written the equation for the force of attraction between the top stator and top rotor poles. But we have B is equal to mu 0 H. So we can rewrite this equation as B is equal to mu 0 into mmf by Lg. That is equal to mu 0 into AT by Lg. AT means mmf. So you can write F1 is equal to half mu 0 AT by Lg1 the whole square into A by mu 0, where A is the area. What is equal to half mu 0 AT by Lg1 the whole square into A. That is the equation for the force of attraction on the top portion of the air gap. The force of attraction between the bottom stator and rotor poles, that is F2 is equal to half B2 square by mu 0 into A. Here the only difference is in the flux density, that is B2. This is because the difference in the air gap length. Here the air gap length is Lg2. So the equation for F2 is equal to half mu 0 into AT by Lg2 the whole square into A. Since the air gap length Lg1 is greater than Lg2, from equation number 2 and 3 we can say that the force of attraction F2 is greater than F1. This is due to the unbalanced magnetic pull. Thus, a resultant radial force or pull acts in the downward direction, and this force is called unbalanced magnetic pull. Now, let's discuss the practical aspects of unbalanced magnetic pull. While designing electrical machines, the following aspects must be taken into account. There are three cases. First one is the unbalanced magnetic pull is very large in induction motors since it has a very small air gap length. As compared to other machines, induction motors have a very small air gap length, so the effect of unbalanced magnetic pull will be more in induction motors. So utmost care must be taken into account to keep this air gap uniform. If there is a small, very slight change in the air gap length, then the effect of unbalanced magnetic pull will be large, very large. So the conditions to keep the air gap length uniform are use ball bearings. Second one, stator windings having parallel paths with equalizer connections. And third, rigid and short shaft. By using a rigid and short, very short shaft, the bending or tilting of shaft can be very much minimized. And second case to be kept in mind is certain combination of a rotor and stator tooth produced noise and vibrations. So it should be kept in mind while designing the electrical machines. And third one, due to the asymmetry in the air gap, that is the difference in air gap, there is a considerable homopolar flux produced in two-pole machines. This may cause an EMF to be induced in rotor bars of induction machines. So in order to avoid this situation, we have to use stator windings having parallel paths with equalizer connections. Thank you.